Right, morning everyone. Apologies for the technical issues. My name is Andy Younger from CEFAS in the UK. I'm going to talk about strategies to reduce norovirus from contamination from bivalve mollusks and specifically Pacific oysters. So depuration, just to explain what that is, it's a treatment process for Class B shellfish under European legislation. And effectively for that, you're purifying your shellfish in tanks of clean seawater. Quite a simple process on the face of it, but there are various things that can go wrong in the process. It's intended for microbiological contaminants rather than chemical contaminants. That's the key thing to note here. And whilst it's very effective for bacteria, E. coli is pretty well removed. It doesn't work so well for viruses, and we've seen that time and again. And this is something that EFSA, the European Food Safety Authority, recognises, that depuration doesn't work so well for norovirus. There's no standard in the European legislation at the moment for norovirus, although I think one is in the pipeline, although it probably won't happen very quickly. A putative standard has been put forward, but nothing in legislation as yet. And essentially what this means at the moment is that we're doing everything on E. coli. That's the statutory indicator, and unfortunately we see shellfish that are free from E. coli but can still cause norovirus illness outbreaks. And norovirus is probably the most common cause of illness associated with shellfish across Europe and probably the world. It's a relatively mild disease, diarrhea and vomiting, but not very pleasant. 2 or 3 days of being close to the toilet, and obviously involves a lot of lost sales. So it's a big issue for the industry. Now, I have done some work on this previously, looking at elimination of norovirus. If you look at the green lines on this graph, that is norovirus at 2 temperatures, 8 and 16 degrees in this case. And you can see even after 14 days, there's no or very little removal, perhaps a little bit at 16 degrees. Just draw your attention to the yellow line. That's a virus indicator that FRNA bacteriophage, very similar to norovirus, but the advantage of that particular one is we can grow it, and that's what we can do for this trial. We're going to see if we can compare norovirus removal with FRNA phage. The problem is we can't grow norovirus, and so we use bacteriophage which we can grow to see how the norovirus might be behaving. But what we need to do is to see whether the FRNA phage is the PCR signal, which is what we're using for norovirus, is the same for FRNA phage. So this trial will investigate that issue. It'll all become clear as I go through. So the key question is how much of the norovirus that doesn't seem to be removed, how much of that is still viable? So the aim of the study then is to develop an enhanced depuration-based procedure for removal of norovirus and to look at the infectivity of norovirus using this FRNA bacteriophage indicator. This is something that's needed by the shellfish industry, particularly in the winter, which is the peak norovirus season. The various challenges associated with this study. So the current norovirus test method is what's called a PCR method. So it's a molecular-based method. It cannot indicate live or infectious virus. It's just looking for a little bit of genetic material. And obviously it's the infectious virus that's the risk to the consumer. Now this surrogate virus that we're talking about, FRNA phage or FRNA bacteriophage, it goes by various names. I'll call it FRNA phage just because it's a bit easier to say. So that can be used to indicate infective norovirus risk. That's certainly been used in the environment, but in depuration conditions, it's still a bit uncertain. So we looked at that in this particular trial. And the advantage of using this FRNA phage is that it's easy to grow. So we've got a viability test for it. And what we're also going to do with this test is to do the PCR test similar to the norovirus test to see whether there's a difference between the PCR result for FRNA phage compared with the viability result. And by making an assessment of those two results for the FRNA phage, we can perhaps extrapolate to what might be going on with norovirus. We can see whether the genetic material is being removed or not by the PCR method for norovirus, but we don't know about infectivity. So we're hoping to use phage for that assessment. So the methods, we looked at Pacific oysters, as I say, which is the main species that's associated with illness from norovirus because of oysters being generally eaten raw or lightly cooked. We used environmentally contaminated oysters, so oysters that were placed near a sewage discharge. And we looked at various factors. So we looked at temperature, 18 degrees versus 8 degrees. We looked at feeding, using microalgae grown in the lab, and also a commercially available preparation of algae. We looked at light versus dark regimes, disturbance versus non-disturbance, and that's really just the vibration associated with the pump, and then having a tank that didn't have a pump, just to see whether that was affecting the shellfish. They're quite sensitive creatures. And looking at continuous flow of water through the tank versus recirculation of unfiltered seawater around the tank. And as I say, we tested the oysters for norovirus using this PCR method, looking for gene groups 1 and 2, which are the most commonly associated with human illness. And we looked at FRNA phage by culture method, as I say, and by PCR, so the same sort of method as for the norovirus. And we also looked at E. coli just to, that is the statutory indicator, just to make sure that that was being removed. And the tanks here on the right, these are the tanks we use. These are commercially used in the UK, certainly. They're relatively small tanks, just 90 kilograms of oysters or mussels, but they are commercially used tanks. So here are the results. It takes you a while to get your eye in here, but along the bottom is time during the purification cycle, and the left-hand axis is the concentration of the various things we're looking at here. So the straight line, the continuous lines are norovirus genogroup 1, and you can see there's very little removal after well over 100 hours. So not much in terms of removal for norovirus genogroup 1, which was disappointing. But the dotted line represents genogroup 2, which shows much better level of removal, particularly at 18 degrees, which is the red dotted line. Now the dashed lines represent FRNA phage, which is our virus indicator, and the fact that that's more easily removed or better removed than both the norovirus gene groups suggests that perhaps FRNA phage isn't such a good indicator under depuration conditions after all. I have to say though that the results, the levels we had, were relatively low during the trials, even before depuration. So we are going to be confirming this by further work just to see what was going on there. It may just be that because we're near the limit of detection of the test, that the results for the FRNA phage weren't as reliable as they could have been. So in terms of conclusions from this study, we found that depuration was twice as good, effectively, at 18 degrees than at 8 degrees after 5 days. Now, a normal depuration cycle is, say, 2 days, probably occasionally 24 hours, depending on whereabouts in Europe we might be. But certainly, so extending depuration and increasing temperature seem to make a big difference. We found norovirus genogroup 2 was much better removed than genogroup 1. Now, genogroup 1, we have seen colleagues in Ifremer in France have done work looking at binding of genogroup 1, norovirus genogroup 1, to the oyster gut. So there may be a binding issue here, which is preventing the genogroup 1 from being removed. Certainly genogroup 2 levels were reduced up to 60%, which is a pretty good level of removal. So, so that was encouraging. So it does suggest that depuration is useful for some strains of norovirus. Cool. We also found that salinity, which is one of the factors we looked at, that does need to be matched to the natural environment to which the shellfish are acclimatized. So within about 20%, we think is probably what you should be aiming for. And surprisingly, perhaps the other factors trial didn't seem to make much difference. And that included feeding. We were expecting feeding to make some difference, but it didn't seem to significantly improve removal at all. And as I've mentioned, FRNA phage did seem to get removed in our study in both gene groups for norovirus. So we need to do further work on that. So we couldn't really assess infectivity of norovirus in the way we had planned. I would say though that for the FRNA phage results, both the viability assay and the PCR results were fairly similar in terms of removal, which does suggest that there was removal of FRNA5 rather than in situ inactivation, which could mean that the norovirus results we've seen previously were reflected the infectivity as well. Oh yeah, just to point out that E. coli was consistently removed in all the trials as we'd expect. So the summary outputs, elevated temperatures can lower norovirus levels from contaminated Class B oysters. And this is, of course, assuming temperate climate similar to the UK. We wouldn't like to make assumptions for hotter climates such as the Mediterranean. It is relatively cheap to add heating to systems, according to figures we've obtained. So 35 euros, for example, for the system we use, the 90 kilogram system, maybe 450 euros for a bigger system, 750 kilograms. So not massive expense when you consider the benefits potentially of in terms of norovirus removal. This method can help reduce risks by improving food safety, and obviously anyone can use this method. It's relatively straightforward to implement. We've produced a paper on this in Food and Chemical Toxicology. We've also produced a protocol for the industry to use, which is freely available from the Seafood Tomorrow website. And that's it. Thank you very much for listening.